Okay, so thank you for the introduction. I'm Naoaki Okazaki from Tokyo Institute of Technology. It's my great pleasure to give a talk at this conference. And I wish I could go to Manchester, but I was stuck in Japan this time for the class. So today I'm presenting our attempts about controllability, faithfulness, and explainability in natural language generation. Nowadays, various tasks of natural language generation are modeled by sequence-to-sequence architecture. So in this slide, I will give an example of training a language model with transformer decoder, a well-known architecture of sequence-to-sequence. Although our studies to be presented later use the encoder decoder of transformer, I will use transformer decoder in this slide for simplicity. The task of language models is to predict the next word given a context. For example, this model predicts the next word upon based on the context once. And this model predicts the word there based on the context once upon a time. We represent a context with a sequence of token embeddings, and then we feed these token embeddings to the model, and then compute the probability distribution of the next word. And when training this model, we update the parameters inside the model so that the probability distributions are close to the empirical distributions or supervision signal of tokens. And we can use this model for conditional generation tasks like machine translation. And this is an example of English to Spanish translation. We give this is a pen dot to es as a context and then ask the model to predict the Spanish word one by one. We predict a sequence of tokens until the model predicts EOS, a special token indicating an end of sentence. In this study, the model can translate this is a pen into esto es una pluma. In order to realize a model that can translate, we give parallel corpus as a supervision data where source sentences and their translations are paired. We tune the model parameters so that the predicted probability distributions of translation words are close to the empirical distribution or supervision signal. And we can use the same architecture for various tasks. And GPT is a very popular language model trained on an extremely large corpus. And this approach is called pre-training and fine-tuning. And this is a standard and generic approach for solving various NLP tasks. Although the sequence-to-sequence models are successful in various NLP tasks, they are black boxes trained with huge data, as Sophia explained in the introduction. Sequence-to-sequence models require huge supervision data, for example, more than 1 million sentences pair for machine translation and summarization. Because the models are trained to mimic generations of supervision data, there is no mechanism to control generations. In addition, researchers reported the scaling law, which states that the model performance is improved when you use more data, more parameters, and more computation resource. When the model becomes huge, it is difficult to analyze the behavior of the model or why the model generates this output. So instead of splitting the task into subtasks, the model directly learns a task in an end-to-end fashion. So in this talk, I will present 3 studies for considering controllability, faithfulness, and explainability in natural language generation. At this moment, we do not arrive at a state where we establish consistent methodologies for these goals. Instead, I will explain 3 studies briefly to present our work for natural language generation. The first part is related to the controllability of language generation, or can we change the behavior of the model for desired output? The second part is related to faithfulness of language generation, or can we prevent hallucination or fake output? The last part presents an example-based grammatical error correction as an approach for explainability in generation. So let's start the first part. In the first and second parts, we address the task of headline generation. Given an input text like this one, an headline generation create a very short summary like this one. This task is a kind of abstractive summarization where we want to generate new sentences or phrases that do not appear in the input text. Usually, a headline generator is modeled by a sequence-to-sequence architecture such as transformer, where in machine translation term, source text corresponds to an article and target text corresponds to headline. The headline generator is trained by news corpus with more than 1 million pairs of articles and headlines. Here, I want to explain the motivation why we need to generate headlines automatically and to control output length. This slide shows how Japanese newspaper company create a headline. They create 5 kinds of summaries for an article at most. The first one, print, is used for newspaper as shown here. So they do not have a strict rule about the length of the headline in newspaper, but the desired length is up to the layout of the paper. The second one, thumb, was used for the digital signage in trains, or more specifically, Super Express in Japan. However, it was discontinued because everyone nowadays uses smartphone to read news. But the important point here is that the company has a maximum length for the thumb, which is 50 characters long. The third one is called large. This is used as a headline on their website, like this one. The maximum length is 26 characters long. The fourth one is middle, which is used in an access ranking of their website. The maximum length is 13. And the last one is called short, whose maximum length is 10. So in this way, the company creates different summaries for different target media. We usually train a sequence-to-sequence model on news corpus with print headline. And this is because print headlines are the most abundant. A newspaper company writes 5 kinds of headlines like print, some, large, middle, and short, for a limited number of articles. And the news corpus usually includes headline of diverse length. And the length of a generated headline is determined when the sequence-to-sequence model predicts EOS token. However, there is a large variance in length between reference and generated headlines. And this graph shows the histogram of generated output based on the difference in length between the reference and generated output. And this is very close to the normal distribution with mean 0. But we observe large variance between the difference of length between reference and generated output. So we need an additional mechanism to control an output length. And there are these are the previous approaches to control output length. The first one append a special token at the beginning of an input sequence. The length of the headline of this example is 3. So we append the special token 3 at the beginning so that the sequence-to-sequence model can run representations for the controlling the output length. However, this approach is inflexible to generate an unseen length. In other words, this approach requires supervision data for each desired length to obtain the representations of the special tokens. The second approach multiplies hidden vector with the desired output length. So in this example, where we want a headline of 3 tokens long, we multiply this hidden vector with 3. We expect that the norm of the vector gradually decreases as we compose the internal hidden vector in the decoder. However, it is impossible to control the remaining length exactly at each time step of the decoder. For this problem, we propose a very simple approach for controlling output lengths. So we modify the positional encodings in the decoder of transformer so that we can tell the remaining length or the target length at each time step. Suppose that we want to generate an output of 3 tokens long. So we tell the decoder that the number of remaining tokens is 3 from this time step. In the next time step, we decrement the number and tell the decoder that the remaining length is 2. And in order to realize this, we don't have to introduce embeddings for special tokens. We just change the formula for computing the positional encodings in the transformer. But I won't go into the detail in this presentation. So what we need is to change a few lines of code in the transformer implementation and train a transformer model with modified positional encoding. So in this way, we can guide the decoder to consider remaining lengths when predicting every output token. So in order to highlight the changed part from the linear transformer, please take a look at this part. So in the original transformer, positional encoding starts at 0 and increment the number at each time step. However, we cannot tell the decoder the remaining number of tokens if we use this architecture. So this is a changed part. So this is our proposal, and this is the linear transformer. This table summarizes Rouge scores on JAML, and JAML is a Japanese news corpus. And this is a Rouge score of the baseline models and the proposed model. And these are the Rouge scores when the target length is 10. And these are the Rouge scores for the target length of 13 and the target length of 26. And I want to go into the detail of the baseline models and variants of the proposed method, but we observe that the proposed method improves Rouge scores compared with the previous approaches for controlling output lengths, len init and LC. And these are the results when proposed method was trained on the dataset without a headline of the target length. So as we can see, the proposed method worked well, even if the training data does not include the target length. And this table shows the variance of length between the generated and reference headlines. In this experiment, we use character-based tokenization in the decoder for the precise control of length. And we observed that the proposed method outperformed all baseline in terms of precise control of length. So the variance of the length between reference and generated headlines are around 0. In addition, the proposed method again worked well, even if the training data does not include the target length. So this is a summary of the first part, and I demonstrate that the proposed method could generate a headline of higher quality, precise length control, and the proposed method worked well even if the length was not seen during the training. And we can also apply this technique to combine machine translation task and automatic summarization. So we can consider cross-lingual automatic summarization, and we present this work in LLEC, which are now happening in the conference. So this is the second part about faithfulness of language generation. And this slide shows examples of headline generated by UniLM, which was the state-of-the-art model for headline generation. This model achieved 38.9 Rouge score, which is still close to the current state-of-the-art performance. As you can see, the generated headlines are very fluent despite the relatively low Rouge score. However, if we look at this headline more closely, we notice some problems. The first headline includes phrase in November, but we cannot find the corresponding information in the input. So phrase in November is based on the bold guess of the model. The second headline mentions the news source as the Detroit News, but this is incorrect. The third headline, English Football League tables, is nothing to do with the input. So in this study, we define the term truthfulness as whether all facts of a generated summary are mentioned in the source text. An untruthful headline causes a serious problem like fake news in the real-world application of headline generation. So in this study, we hypothesized that an untruthful headlines are caused by the flawed task setting of headline generation. In the task of headline generation, source articles are usually trimmed before training a model because of the restriction of GPU memory. And we cannot observe any improvement in root score even if we use longer input. So trimmed source article may be insufficient for generating headline. For example, if we trim the source article into a lead sentence, then we lose the sentence. There's not much time left, the mayor said. And this is necessary to generate the phrase a little time left in the headline. However, we had to repeat the same experimental setting because the researchers compare root score in the same experimental settings. So we measure the truthfulness of actual headline written by the newspaper company. So when we use the full articles as the source, information necessary to generate headline is mostly covered. However, if we trim source article with the common procedure, for example, 1 lead sentence for gigawatt and 3 lead sentences for Japanese news corpus, source article can cover only 70% or 60% of the information of headlines. So we concluded that common experimental settings or trimming is a cause of untruthful articles in training data and the trained model. So the idea explored in the study is very simple. So we build an entry-element classifier to judge whether a source article covers all information in the headline. If the classifier predicts a positive or a pair of an article and its headline, the source article contains sufficient information to generate the headline. If it predicts a negative, then the source article lacks some information to generate the headline. So we use the entry-element classifier to filter out insufficient article from the supervision data of headline generation. So in this way, we can build a clean supervision data where source article contains sufficient information for headlines. However, this reduces the number of training instances of headline generation. So in order to compensate the reduced number of training data, we also use self-training strategy to generate pseudo headlines from discarded articles. So this table shows the experimental result of English Gigawatt and JAMU, Japanese News Corpus. And these are the root scores, and SUP stands for support score that measures the truthfulness of headline based on the word overlap between headlines and source articles. Entail stands for the ratio of headlines entailed by articles judged by RT classifier. And truthful stands for the ratio of headline entailed by article judged by human evaluator. On English Gigawatt, filtering training data resulted in lower root score than using the full data. However, self-training strategy was effective, achieving the better result on the full data. In contrast, on JAML dataset, filtering training data again resulted in lower Rouge score than using the full data. In addition, self-training could not improve the Rouge score, probably because the training data was too small for building the initial headline generator. An interesting result is that on both datasets, filtering training data improved the truthfulness of headlines. And this also suggests that Rouge scores cannot measure the truthfulness of headlines. So we may need to evaluate the relevance based on Rouge score and truthfulness with these metrics. After doing this experiment, we asked a news media company to verify the usefulness of headline generation in newsroom. So we asked Jiji Press to conduct a demonstration experiment that provides and distribute short summary by using an editing headline generated by the API developed by us. So we asked them to use our headline generator, and then the news reporter write a headline based on our result. And this is a ratio of the evaluation of our generated headlines. A means perfect, so nearly perfect, and B means this is beneficial, even though they have to edit some parts in generated headline. And C means it may take time to write headline from scratch, but the headline is still useful. D is not so useful because the news editor took longer time than writing from scratch. And E means there was some untruthful or fake information in the headline. So in total, we received that 80% of headline generated by our method is useful. And if the news headline is categorized into A, then this headline may be broadcasted in digital signage in Shibuya like this. Okay, so we came to the last part. And this is the work for explainability of language generation. As I explained before, language generation is a black box. So most studies achieve good performance by end-to-end learning with huge supervision data and model parameters. For this reason, it is difficult to interpret why the model generates an output. At the same time, explainability is important for some generation tasks. In machine translation, we may want to know why the model chooses the word for the translation. In the response generation of a dialogue system, we may want to analyze why the model generates the response for the utterance. There are some previous approaches for interpretability of neural network models. Model visualization shows embeddings, attention map or saliency map in the model, but this is too difficult for an end user. The lexicalization replaces, for example, nouns with template variables, but this degrades the performance of the original model. So next, I will explain the task of grammatical error correction, or GEC in short. A GEC system receives an input text from language learner and then revises the input text to reduce the error in the text. So in this task, a language learner not only uses the output text, but also want to know the reason behind the edit to improve their language skill. In this educational scenario, explainability is important. For example, it is shown that an example of correct and incorrect sentences were shown to be effective for language learners. So in this research, we are interested in presenting a pair of incorrect and correct sentences that is relevant to the revised output. However, GEC is again modeled by the sequence-to-sequence architecture, which is a black box in general. So in this study, we consider using the architecture of nearest neighbor machine translation. So this is a relatively new variant of sequence-to-sequence model that improves the performance of neural machine translation using the translation example related to an input. In nearest neighbor machine translation, we extract the representation or hidden vector and its output token of each time step in the decoder during training. We store the representation as a key and output token as a value in the database. When predicting a token, the decoder composes a hidden representation and retrieves entries whose representations are close to the current hidden representation. So in this figure, we consider this French sentence as an input, and the decoder has already generated the sequence of English words. This is the current representation of the decoder, and we want to predict the next translation word. In the nearest neighbor machine translation, we retrieve entries whose representations are close to the current representation. In this slide, we found these entries. These entries correspond to these translation states during the training. We rerank the translation words based on the closeness of the retrieved and current vectors and build a probability distribution like this one. And finally, the translation word is determined by the interpolation between the vanilla sequence-to-sequence model and the probability distribution computed by nearest neighbors. So in this study, we adapt nearest neighbor machine translation to the task of grammatical error correction. This is the input to the Jiji system. The decoder has already generated a sequence they had as a partially revised sentence and want to predict the next word. The vanilla sequence-to-sequence model computes a probability distribution of output token like this one. In addition, this model retrieves nearest neighbor example in the database and then obtain a probability distribution computed from neighbor examples. By interpreting these distributions, the decoder predicts an output token like but then the proposal of this study is to use the closest example as an explanation of the correction of GEC. So in this slide, this example corresponds to the training instances with these correct, incorrect, and correct sentences. So we present this pair to a language learner in addition to the revised sentence. So we evaluated the usefulness of the example presented to the language learners. The token-based baseline retrieves example from training data by using surface match. The BERT-based baseline retrieves example based on the similarity between contextualized token representations. This table shows the percentage of useful example presented by these methods. And this is judged by language learners. As shown in this table, the proposed method EBGEC was better than these baselines. The language learner answered 70% of examples presented by the proposed method as useful. We could also observe the performance improvement of the grammatical error correction, except for JFLAG dataset. This result is consistent to those reported in machine translation research. And this graph shows the performance when we change the value of lambda, the coefficient for the interpolation between the translation and neighbor models. And lambda 1 means that we don't use the MT model at all, but we only use nearest neighbor model. And values around 0.25 or 0.5 obtain the good scores. So this is a summary of my talk. So I presented 3 studies towards controllability, faithfulness, and explainability in text generation. And future work includes more work on controllability with different aspects like content, style, or hallucination. And we are also interested in considering integrating controllability and explainability. For example, you want to control language generation model via example or generated example. So thank you very much.